Hi, I'm Mr. V. This is Illustrative Mathematics, Unit 5, Solid Geometry, and we're on Lesson 10, Cross Sections and Volumes. By the end of the lesson, you should be able to say, I know that if two solids have equal area cross sections at all heights, they have the same volumes. And our first question is, these images show the same number of coins, 17 quarters. You can see by the ridges, they're quarters, and they have a copper lining on the outside. 17 coins arranged in different ways. They're the same number of coins. How are the two stacks different from each other? Does either stack of coins resemble a geometric solid? If so, which one? How do the heights of the stacks compare? How do the volumes of the stacks compare? And most students that did this activity could say that they have the same number of coins, so the first one is like a cylinder, and the second one is like a slanted cylinder or a tilted cylinder. The technical word that we use is oblique when its bottom base and its top base are not perpendicular to each other when they're skewed, if you want to say, they're slanty. We call this oblique. That's the technical term. How do the heights compare? Well, they're both 17 coins high, so they're both the same height, even though this slant height here is longer than straight up and down. If you were to draw this as a right triangle, you would see that this is going to be like a hypotenuse, and it's going to be longer slant height, but the actual height going straight down is the same. How do the volumes compare? They're the same. And you'll notice that the cross sections at each point, these are a circle. This is not going to be an oval. They're all circles. They're all the same coins. So one stack is right, the other one is oblique. You concluded that the volumes are equal, even though the stacks are different. They both have the same base. They're the same overall height. This leads us to Cavalieri's principle, which is the idea that solids of equal height have the same volume if all their cross sections at all levels of height are the same. Prisms and cylinders are said to be oblique if one base is translated to coincide with the other by a directed line segment that defines a translation that is not perpendicular to the base. So it goes like this. What geometric solid does the stack of cards represent? It represents a right rectangular prism. And what is the shape of the base? It's a rectangle. And if you take any cross sections parallel to the base, it's a rectangle. So if you shift it, it's going to make it an oblique rectangular prism. Does it change the volume? No. And here's an example. If I did the cards like this, I could cut it and then move it, and it would still be the same. These are the same volumes. Now I have a demonstration here with regard to this that I'd like to show you. This is from GeoGebra, and where is my GeoGebra? Here it is. And I'd like to show you. Here I have two rectangular prisms, if you want to say. They're both rectangular. They're rectangular prisms. It's not square. And if I move these to be lined up with each other, I need to move this thing out of the way. Pause this, move this thing out of the way. You can see that if I move the base, the plane, they're both the same all the way up. And if I scoot this one over a little bit and I move the plane, I can draw it. They're all the same. They're both rectangles all the way up. And you can look at it from above, or you can look at it from different angles here. Now, if I take this blue one and the green one, and I make it an oblique prism, so it's the same, but all of the surface areas all the way up are the same. These still have the same volume. You can see that this slant height here is a lot longer than the actual height, but the actual height is from this point straight down, not along the slant. That's kind of significant there. Let's see. Going back to our Desmos. Cross sections of an oblique prism are rectangles, not prisms. They're not like parallelograms that are not rectangles. They're rectangles all the way up. If we have cards, think back on the coins. This just didn't make the, just because we made it oblique didn't make them ovals. They were still going to be round all the way up. So when we shift to cards so it's oblique, did the volume change? No. Can you explain your explanation in terms of cross sections? All the cross sections were the same all the way up. What if we had a stack of circular cards and each circle had the same area as the rectangular stack? How would the volume of these two figures compare? And let me see if I can make this. So here I have a circle, a circular base, and a rectangular base. This has a base area of B, and this is a base area of B. And if you cut it anywhere along that same parallel to that same base, it's going to have B for both of them, and they both have the same height. So these two figures, even though they are very different in shape, since they have the same area of the base all the way up along the height at all different heights, by Cavalieri's principle, they are the same volume. Cavalieri's principle. If two solids are cut into cross sections by parallel planes, and the corresponding cross sections on each plane always have the same area, then the two solids have the same volume. And that's kind of curious and it's kind of strange to do. Now, all this time we're going to do different pairs of students would do these problems. I'd like to point out to you here, the base of this is 4 times 3, which is 12. Base of this is 12. The height is 6, and the height here is 6. So these two are congruent. They have the same, not congruent, they have the same volume. Their volumes are equal. These two, you may think that they have the same, but if you think about your coins, this is a higher stack of coins than this one is. This one has a height of 7. This 10 is not meant to confuse you. It's just to show that the slant height is 10, not the actual height. The actual height here is 7. So even though the bases are the same with a radius of 3 and it's a circular base, it would be 9 pi. It's 9 pi here, and all the way up it is, but this one doesn't go up as high. Not congruent. Not equal volumes. These both have equal volumes. They start with a base of 9 pi. They go up 5 in height to a point. So at each pace along the way, they're all circles with the same areas. This one you might think of as not being the same, or maybe it's the same. I'd like to show it to you if I can on my whiteboard. We have a triangular piece here on the end. This is a triangle. And the area of a triangle is 1/2 times the base of the triangle, not to be confused with the base of a prism, times the height of the triangle. So that's 1/2 times 3 times 4, which is 6. Oh, and look, the base of this is also 6. So it's 1 times 6. So if I stand this up on its end like this, make it a triangular prism, and the base here is going to be an area of 6, all along the height, and they both go up to a height of 5. These two figures, by Cavalieri's principle, have the same volume, and that's kind of important. So let's see. If I flip this pyramid, it has a base of 5 by 5. This has a base of 5 by 5. This one goes straight up. This one is oblique, but they both go to a point that is 5 above it. This one is a right one. It goes directly up above the middle. And so these two have the same volume. These two don't. One is a cylinder. The other one is a cone. It goes to a point, not to a base that's identical to it. And here are the answers to each of those, with explanations. Lesson synthesis. Can you identify a cylinder that has the same volume as this one? Well, if it's right, it's going to go up 25 straight up instead of up 30 at a slant. And which number would I not use in the volume calculation? I'm not going to use this 30. I might later on give you an angle and this hypotenuse and ask you to find the height to find the volume. But right now, the only numbers I need are the 25 and the 10. How would I do this in my head? Pi r squared. 10 squared is going to be 100. So this would be 100 pi times 25. That's 2500 pi. That's how I would do it in my head. In this lesson, you explored right and oblique, and as related to Cavalieri's principle. I have a thing here on Cavalieri, Bonaventura Cavalieri. He was a monk, a Jesuit monk, lived from 1598 to 1647. So he lived back in some of the days of some of the greats. And you might think, well, duh, yeah, you move it over sideways, of course it's going to be the same volume. But what Cavalieri did was he proved it, and that was what makes him stand out and different. Proving is a little bit beyond the scope of this course, so we're not going to do that. Earlier, we established that the volume of a prism or a cylinder is equal to the area of the base, capital B, times the height. And what Cavalieri's principle does is it allows us to be used when it's oblique, or it expands our knowledge and our ability to use this. If you had a stack of papers, you could slant them. This works whether you have a cylinder. We have two figures that are very different from each other, but if they have the same cross-sectional area, like we did earlier, we have a cross-section of 6 here. If this is the same area as this one, then these would have the same volume. And here you can see that this is a right pyramid. It goes straight up the middle, and this one is oblique. We will use this oblique business of the pyramid later in coming to understand how this is the volume of a pyramid is 1/3 the area of the base times its height, as opposed to like a prism, which is the area of the base times the height. And the last page is for you to draw two figures. Hopefully you would draw them when they have the same identical areas, but maybe you would draw one that is not oblique and one that is oblique. Anyway, that's all I've got for you today. Good luck and success.